Hello, welcome. Today, my goal is to tell you a little bit about the expectations for learning in this class and in general in college classes, and also address Learning Objective 5 Vectors and Sequences Challenge. So, to begin with, I want to talk about the four levels of competence here described in this pyramid. The bottom here is unconscious incompetence. I don't even know what I suck at. Then you go up there to now I know what I suck at, and I can do the task, but with effort. And then finally, the last stage is unconscious competence. I can do it without thinking. Think, for example, speaking. Now we can usually we learn as babies. We are at the very bottom level here. We don't even know how to do it, and what are we supposed to do. But then later, right now, we're usually at the unconscious competence level. It's helpful whenever you think about how good do you know a certain skill to kind of think about this pyramid and to think, where am I at? Another level of depth for any thinking is looking at this Bloom's taxonomy. So any skill, anything that you learn, um, especially in mathematics, you should be thinking about it from this pyramid's perspective. So at the bottom layer here, it's remembering, where you just recall facts. You know the definition. What is a dot product? What is a cross product? What is a vector? What is a sequence? What does it mean to converge? And things like that. You're just remembering facts. And then you go up to understanding, where you can explain ideas or concepts. Um, and here is basically you're putting together all these facts and trying to make sense of them and connect them up. But then you have applying, where you use information in new situations to solve questions about it. So solving questions that you haven't seen before. A step above that is analyze, where you draw connections among ideas, and then evaluate, justify a stand or a decision, and then create, where you produce new or original work. It's helpful when thinking about Bloom's taxonomy to have examples in mind for each of the kind of questions that apply to each level of the taxonomy, so that you can determine where you're at with any skill or thing that you're learning. Um, so one example I provide here is Bloom's level of learning applied to Goldilocks and the Three Bears. This is a story for children that I had not known before coming to the United States, so I had to learn to read this, but now I know it because I have children. So take a look at this example, because this might really resonate with you, and you might understand the different layers here much better. An example related to directly to this objective, I also applied it to the cross product, and I put an example question for each level here. And you can access all of this, what I'm showing here. You can access it in, if you go to the class notebook, student hours, learning objectives. All of this is in there, and you can kind of sit down and read through it. But with that in mind, ask yourself, what are the type of questions that you're tested or you're expected to understand in high school versus college? What's the difference? Where are those located in this Bloom's taxonomy? So, um, so I want you to pause the video and think about this for yourself. Uh, in general, like most high schools are at the understanding and remembering levels of the taxonomy, and they focus really mostly on remembering a lot of facts. But then they also ask questions on apply and analyze, perhaps, but it's rare. In college, though, there's a big jump that happens, you're expected to be somewhat in the middle of this Bloom's taxonomy. So whenever you're learning stuff, you're expected to be able to use it in new situation. You're expected to draw connections among ideas, and sometimes you're even asked to justify a stand or produce original work, but those are rare. Generally, these top two layers are reserved for graduate school. Although you could still ask meaningful questions from these two layers that are not graduate school level. And so in this learning objective, I focus mostly on the top half of Bloom's taxonomy, and I ask questions related to these layers. The questions I put here in this example are mostly graduate level kind of questions that you'd ask for the creating and evaluating part. Although you can think about those right now as well. There's nothing stopping you. I rated each of the sample questions here into one of the layers of Bloom's taxonomy, so you kind of have more examples and ideas about what am I exactly looking for this learning objective. I want to solve the question first and the third sample questions here. Find two vectors with a dot product of 10 and explain what the dot product means geometrically about these two vectors, and find two vectors that have a cross product of 0, 0, 3, and explain what the cross product means geometrically about these two vectors. Now, you could solve each of these questions individually, but I want to make my life a little harder, and I want to solve both of these at once. I want to find two vectors with a dot product of 10 and a cross product of 0, 0, 3. And to do that, I'm going to think about, okay, so what does it mean for a cross product to be 0, 0, 3, for example? What does it mean for a dot product to be 10? So you really need to be thinking about, have those geometric definitions in mind. You could think about this strictly using the symbolic definition, the algebra definitions, and you might come up with some equations that you need to satisfy and solve. And that will be a little bit harder to think about, but it's not undoable. You could do it that way. The geometric way of thinking, I think it's much easier and better. So I'm going to think of it from that perspective. So what does it mean to have a dot product of 10? It means that when you project one vector onto the other and scale by the magnitude of the one you're projecting onto, you get 10. That looks quite complicated. Okay. So, and we don't know what two vectors we got. There's infinitely many vectors that for which this could possibly happen. Okay, so let's think about the cross product. Cross products are more limited because they only work for three-dimensional vectors. So whatever vectors we're trying to find, they're three-dimensional, and I want my cross product to be 0, 0, 3. Notice here I'm not using 0, 3, 0 because of a mistake I made when solving this question, but there's nothing wrong with 0, 3, 0 here. I'm just going to focus on 0, 0, 3 instead. So what does it mean to have a cross product of 0, 0, 3? Well, I can imagine that's going to be this blue arrow here on the side, and it's going 3 up in the z direction. And what that means, like, what two vectors could produce this when you cross product them? Well, the two vectors that I need must be perpendicular to the cross product. So if we fix their starting point at the origin, they must then lie on the xy plane. So that's good. That's a lot of information already. We reduced to 3D vectors, and we know they lie in the xy plane, so their z component is 0. What else do we know? Well, the magnitude of the cross product is the area of the parallelogram determined by these two vectors. So if I want to think about, well, area of the magnitude of this vector, what is that? Well, it's just an arrow going 3 up, so the magnitude is 3. So I want a parallelogram here of area 3. The easiest example you could think of is it's a rectangle, a 1 by 3 or 3 by 1 rectangle. So if you go 1 in the x direction and 3 in the y direction, this yellow parallelogram has area 3. It's in fact a rectangle, but all rectangles are parallelograms. So then I might think, okay, so that's a good choice. But notice now I want the dot product to be 10. And if I have two perpendicular vectors, like I here and 3j, which form this yellow parallelogram, the dot product will be 0 because they're perpendicular. So I need it to be 10 though. How can I change it? Well, um, area is base times height. I'm going to fix the bases to make things easier. I'm going to let I be one of the vectors. Why do I do that? Well, when I take dot products, I'm going to scale by the vector I'm projecting into. And if that vector, but the magnitude of that vector is 1, then I'm going to just scale by 1, which does nothing. And that means that the dot product of these two vectors, I and whatever other vector I pick, those that will just be the length of the projection of that other vector onto I. And I need that length to be 10. So if I take U and I project onto I need to have that needs to be 10. But that just means that the x component of U is 10. Now, if the x component is 10, that means U could really be anywhere on this x equal 10 line. But I also need the area to be 3. And area is base times height. Base is 1 here, the magnitude of I. And if I think about this yellow parallelogram, if I shear that parallelogram, the height will not change for the parallelogram. So if I shear this parallelogram to say here U, then it will still have an area of 10 because the base is 1, the height is 3. Which means that then I want really my y component of the second vector to be 3. And so that pins down uniquely the u vector. U should be 10, 3, 0. And so checking that my work here on the side, you can do I dot u dot product. So multiply component wise and add. And then the cross product, I cross u, using the determinant, it does check out. That really works out. So I didn't make any mistakes logically, and I got two vectors that fulfill the conditions. So I'm done with this question. Now, I wanted to go back here and talk a little bit about the motivation for this kind of topics that we've talked about, like vectors and dot and cross product and sequences. There's lots of links that you can look at here. If you go to the Canvas Learning Objectives and Questions PDF, I pulled it up here. Oh, not quite. So if you go there, to Learning Objective 5, there's a bunch of links here. This was one of the videos that I asked you to watch, and then there's one on modules, which is an abstraction of vector spaces. And there's lots of, that's even more abstractions of this. So ultimately down the line, you might not need abstract vector spaces, but these other more general vector spaces are what you really need. There's also a link here on a curious pattern indeed on sequences and the Collatz conjecture, which is an unsolved problem. I opened up those in here. There's a curious pattern and the Collatz conjecture. So the